Hello everyone, welcome back to my presentation. I am Sangeeta studying in Sri Venkateshwara College of Engineering from the Department of Computer Science and Engineering. Today we are going to discuss about the concepts regarding microcontroller. And today's table of contents are Introduction to ARM Instruction Set and ARM Processor Architecture, ARM Instruction Formats, Data Processing Instructions, Load and Store Instruction, Addressing Modes in ARM Pipelining Stages, Hazards in Pipelining Techniques to Mitigate Hazards. And today we are going to discuss about the concept ARM instruction and pipeline. These are the basic concepts in microcontroller. First, we will discuss about ARM instruction and then we'll go to pipeline. Introduction to ARM instruction set. Before going to the introduction, what is actually ARM? ARM stands for Advanced RISC Mission. What does RISC stand for? It is a reduced instruction set computer. There are two types of instruction set computer. One is RISC and one more is CISC. CISC stands for Complex Instruction Set Computer. Here we are using RISC machine. So which we use RISC machine in microcontroller will be abbreviated as ARM. The ARM instruction set is a widely used architecture for energy efficient and high performance microprocessor. It provides a comprehensive set of instructions that enable efficient execution of a broad range of applications from embedded system to high-end servers and smartphones. Today, whatever the embedded systems or the smartphones, laptops, computers we are using, everything the instruction set what used is RISC type. ARM processor architecture, core architecture. The ARM processor is based on the reduced instruction set computer architecture. As in the beginning I have told, RISC stands for reduced instruction set computer architecture, which means it has a simple and efficient instruction. The core of an ARM processor contains key components like the arithmetic logic unit, program controller PC, and register file that work together to execute instructions effectively. This is about the core architecture. Next is memory hierarchy. ARM processors utilize a multi-level memory hierarchy, including on-chip caches, external RAM, and storage. So, memory hierarchy way, see the core architecture is where it is a input where it uses program controller and arithmetic and logic unit. These are the basic computer needs which it will be using, and memory hierarchy is where the memory is stored. So first it will be in registers, cache, main memory, flash disk, traditional disk, and at last the remote secondary memory, that is internet. So cycles where the together register and cache is known, it will be on CPU, and the primary storage memories are register, cache, and if we go like remote secondary storage to the register, the accessing will be faster in register compared to secondary storage. But the capacity in the registers will be very low compared to the secondary storage. So in a pyramid, when we go in an increasing order, the accessing will be faster. When we come decreasing order, the capacity will be higher. Next is pipelining. ARM processor employ a pipelined architecture where instructions are broken down into multiple stages that can be executed concurrently. This allows for higher instruction throughout and improved performance. The pipeline stages such as fetch, decode, execute, and write back enable ARM to achieve high clock frequencies and efficient instruction processing. Detailing, we can see the pipelining concept in the next slides. Now, ARM instruction formats. There are actually 3 or 4 ARM instructions format. The first one is fixed length instruction format. The format's length will be fixed. So the ARM processors are in fixed length 32-bit instruction format. So whatever the instructions we are giving for the computer, it should be under the 32-bit. In uniform instruction encoding, the uniform 32-bit encoding ensures that all instructions have the same size, simplifying the fetch decode of the processor pipeline. So So in instruction format, for the best example for uniform instruction is the pipeline. In pipeline, we know there are many stages. For example, we are using a fetch, decode, and execute stages. The three stages should have the same fixed size. It's more than fixed size, it should have the same size. That is, if fetch stage have 32 bit, then decode and execute stages should also have a 32 bit. This type is an instruction format which is known as uniform instruction encoding. Next is instruction fields. The 32-bit ARM instruction is divided into various fields, including the opcode, register operands, immediate values, and addition. Opcode, we give, move, MOV, or add. These are the instruction, and it is known as opcode. Including that, the 32-bit or the fixed length, whatever we have given, that will be divided into several fields, and it will be given to the operands or the opcodes and etc. Next is data processing instruction. Arithmetic instruction. ARM processors support a variety of arithmetic instructions such as add, sub, mul, and divide. These are the instruction or opcodes which is used to perform addition, subtraction, multiplication, and division respectively. These instructions allow you to perform basic mathematical operations. So arithmetic instruction is one of the data processing instructions in the ARM instruction, where it does the operations such as addition, subtraction, multiplication, and division. Next instruction is logical instruction. Logical instruction, as we know, the logic is what we are studying: and, or, not, XOR, XNOR, XNOT gate. These are the logical instructions which can be performed. These are one type of the ARM instruction. These instructions are useful for tasks like masking, bit shifting, and testing flag conditions. Flag conditions we can give if, for example, if Z flag and negative flag, there will be like that. If there is a carry or borrow we have given, the flag should be 1 or 0. These are the some conditions. So in these types of instruction, we use logical instruction. Comparison instruction. It compares one or two operands, whichever the inputs given. ARM provide comparison instruction like CMP, CAM, and TUQ that allow you to evaluate the relationship between two operands. Next, load and store instruction. This is one of the very important instruction in the ARM instruction, where we load some values to one variable and then we store the value to the another variable. So the load instruction, the opcode what we use for load instruction is LDR, and the opcode we use for store instruction is STR. Now we'll see what is load instruction. A load instruction transfers data from memory to a register in the CPU. This is used when the CPU needs to operate on data that is stored in. The general format of a load instruction includes specifying the source memory address and the destination register. So here memory address, we have to give the memory address and the destination register. What is the meaning of destination register is whatever the address we have given, that has to be stored in a particular register. So whatever the register we are storing, that register is known as destination register. So the basic format of load instruction is it holds the memory address and the destination register. Next we'll go for store instruction. A store instruction transfers data from a register in the CPU to memory. In load instruction, we are loading the memory address to a register. And in store instruction, whatever the data stored in that particular register, that will be given to the memory for further process. This is used when the CPU needs to save the results of computation back to memory. Addressing modes in ARM. There are three types of addressing modes in ARM: immediate addressing, register addressing, and register indirect addressing. What is immediate addressing? Where the operand is a constant value specified directly in the addressing. This is useful for loading immediate values into registers. For example, if I am giving add space R0, R1, whatever the value I have given to R0 register and R1 register, it is added and stored in another variable. Or if I give R0, R1, R1, so it adds R0 and R1 and it replaces the R1 and stores the addition. So immediate, I'm giving the directly the opcode there. So these type of addressing is known as immediate addressing. Register address with operand is the content of the register. This allows for last access to data stored in registers which are part of the processor internal memory. A register indirect addressing where the address of the operand is stored in the register. So in load instruction, we are storing the memory address into a register. So storing the address of the operand in the register is known as register indirect address. Next, we are going for pipelining. As we know, pipelining is one of the important concepts in microcontroller and it is very useful. So it saves our time where while one data or one input is fetching, the another data will be decoding at the same time. Whenever there is a fetching of one data and decoding of another data, the third data will be executing and so on. This is one of the important advantages of pipelining. So there are 5 stages in pipelining, namely fetch, decode, execute, memory and write back. Fetch, it fetches the instruction. As we know, fetch means it retrieve the data. Decode, identify the type of instruction. Execute, it performs a specified operation. Memory, access memory for loads and stores. And write back is it updates the registers. Pipelining stages in detail. What does the fetch instruction do? The control unit retrieves the instruction and the program controller is updated. Instead, decode means the fetched instruction is decoded to determine the operation to be performed. Execute, it executes the given instruction. Memory, it involves data transfer. Load or store, the appropriate memory location is accessed. Write back as the results of the execution are written back to the processor's register. This completes the instruction cycle. In pipelining, the instruction cycle is completed in which stage? Write back stage. We'll consider one example for pipeline execution. How does the pipeline works? Here I have given 3 instructions, namely in first instruction add R1, R2, R3. Here I am adding the value, whatever I have given to the register R2 and R3, I am adding that and I am storing it in the R1. Add the content of R2 and R3, store the result in R. In next instruction, sub R4, R5, R6. Subtract the contents of R5 and R6 and the result is stored in the register R4. Next, I am giving load instruction. Load R7, 0 of R8. Load the contents from the memory address in R8 into R2. Here, whatever the contents I have given in the register R8 will be stored into the register R7. So, how does the pipeline processor works? First instruction is add. So first it fetches the first instruction. So it fetches addition, add instruction. After fetching in the second cycle, the decode of addition takes place. Simultaneously, the fetching of the another instruction, that is subtraction instruction, will be fetching. In the same time, simultaneously fetching of subtraction and decoding of addition instruction taking place. It is in the second cycle. And we are coming for the third cycle. We are load. The load instruction is fetching and decoding the subtraction instruction and executing the addition instruction. This is one of the best advantages of the pipelining, where we are executing the instruction simultaneously. After fetching, again all the 3 instructions will be decoded, and we'll see in the fourth cycle the load instruction is decoding, the subtract instruction is executing, and the add instruction is memory. It is in the memory for data transfer. In the fifth cycle, the load instruction is executing, and in the memory instruction there is subtraction, and in the write back stage there is a addition. Write back is the last stage to complete that one instruction. So the addition instruction will be completed in the 5th cycle. And in the 6th cycle, the load instruction will be in the memory and the write back stage is subtraction. So in the 6th cycle, the subtraction instruction will be completed or executed. In the seventh last cycle, there is a write back. In the write back instruction, there is a load instruction. So the load instruction will also be completed in the seventh cycle. Totally in pipelining, there takes us 7 cycles to execute that 3 instructions, namely addition, subtraction, load instruction, which undergoes all the 5 stages of pipelining. What are the hazards? What are the problems coming in pipelining? Data hazards, control hazards, structural hazards. If instruction 2 uses a register that instruction 1 writes to, a conflict arises. Now one register I have used for addition, the same register if I use the subtraction also. While decoding, the computer gets confused and a conflict arises. That is the data hazard. Control hazards due to branch instruction ordering the flow of execution. Structural hazards occur when hazard resources are insufficient. If a single memory unit is used for both instruction and data access, conflicts can arise. If I given a separate memory for both instruction and data, there will be no conflicts in pipelining. But if I give a single memory for both instruction and data, the problem arises because it cannot give one instruction is fetching and again the data has to be decoded in a single memory is a issue which occurs in pipelining. Next is techniques to mitigate hazards. What are the techniques to overcome the problems of pipelining? Pipeline stalling, temporarily halting the pipelining until the hazard is resolved. For example, the data hazard is occurred where I have used the same register name for both instructions. At that time, one of the instruction has to be halt. It has to be wait until that hazard is resolved. That is one of the techniques to overcome the hazards of pipeline. Forwarding, using intermediate results directly from one pipeline stage to another without waiting for the write back stage. Without coming for the write back stage, we are intermediate results we are giving directly in one or the other pipelining stages which comes before write back stage. Branch prediction, guessing the outcome of a branch to continue fetching instruction without waiting for the branch to resolve. Out of order execution, allowing instruction to execute as soon as their operands are available rather than strictly in there. Thank you.